Dear students, now we are going to see the next thing in this stress strain curves, that is the instability in tension. What is this actually? So we know that in the stress strain curve, in the stress strain curve, say sigma t and epsilon, we know that the maximum stress is what? The ultimate stress, isn't it? And after that, the necking is going to start, isn't it? So now the specimen of the material is not going to support for the load, and it is undergoing the necking, isn't it? So this region we know that, say this is the fracture point. So from here to here, this is the necking region, isn't it? Right? So we know that the maximum stress in the stress strain curve is the ultimate strain. And there, if we talk about at this point, see here, so from here to here, from here to here, for every point we are applying the maximum load compared to the previous one, isn't it? And there is, of course, the change in load dP is everywhere here, except at this maximum stress, that is, it is the maximum load here. But there is, if you talk about the change in load at this point, will be what? Because it's a maximum value, it is 0. Isn't it? Change in load at this maximum stress, that is at UTS, the change in load is of course going to be 0. And after that, the material is now unstable. It is undergoing the necking condition, and finally it is going to be get fractured or failed. So now here we know that the epsilon is equal to what? Ln of A original divided by A final. So what is e to the power epsilon? Taking antilog of this, that is A original divided by A final. Or I can write A final is equal to what? A original into e to the power minus epsilon. Very easy, simple mathematics. And here the stress sigma t is equal to what? The applied load P divided by the final or instantaneous area. So here, what is this? P will be equal to sigma t into AF, isn't it? And what is AF? Say from equation 1, we can write P is equal to sigma t into A naught into e to the power minus epsilon, isn't it? This is the P. And what I am saying that at this maximum point of stress, where its change in load is equal to 0, if I differentiate this P with respect to epsilon, that is dP by d epsilon, and equate to 0, what I can write here? Say that is d epsilon of, that is A naught into sigma t into e to the power minus epsilon, and equate to 0. Let us do that. So variables only e to the power epsilon and sigma t. A naught I will take as a constant out. So A naught, and differentiate this sigma t into e to the power minus epsilon by UV rule. Okay. So what the UV rule says? First term into d dx of second plus second term into d dx of first, and equate to 0. So first term into d dx of second, that is e to the power minus epsilon, that is minus 1 into e to the power minus epsilon, plus second term into d epsilon of sigma t, equal to 0, isn't it? So what I can write? This will go here, so 0, so, and this is minus sigma t into e to the power minus epsilon is equal to e to the power minus epsilon d sigma t by d epsilon. So this get cancelled. isn't it? And this is of course positive because this will go that side, so it will become positive. So see here, sigma t is equal to this d by d epsilon, but we know what is sigma t, our true stress, and how to give that true stress by the flow curve equation in this true stress strain curve, that is sigma t into k to the power n, isn't it? Sorry, k epsilon to the power, k epsilon to the power n, that is the value of sigma t. So differentiate this as, of course, k strain coefficient is constant. So what is d epsilon of e to the power epsilon to the power n, differentiation क्या होगा उसका? So it is into n into epsilon to the power n minus 1, isn't it? Is equal to sigma t. But what is our sigma t? So sigma t is, oh no, sigma t is what? K into epsilon to the power n is equal to k into n into epsilon to the power n divided by epsilon. I will write this epsilon to the n minus 1 as epsilon to the power n divided by epsilon. So k epsilon to the power n, k epsilon to the power n get cancels. So n is equal to, what? Epsilon. N is equal to epsilon. So see here, so the value of this strain hardening exponent n here will give you, or whatever the value of this epsilon here at the maximum loading condition, at maximum stress, or at the necking condition in the stress strain curve, the value of strain hardening exponent n and the true strain is same. Please, very important, whenever in the question, in the numerical, they are mentioning like this, at the maximum load, at the necking condition, okay, at the ultimate strength, n becomes epsilon, that is strain hardening exponent, and the true strain value, these are same. Very important. And see, and after that, see, instability is going to begin. That's why it is known as the instability in tension. So for the instability in tension, we are having this relation n is equal to epsilon. Very, very important. Now see students, we are going to see the work in the deformation. The work in the deformation. So again, we are having this stress strain curve, and if I want to find out the work in the deformation, so say this is up to the fracture point, or this is the maximum, up to the maximum strain, say epsilon f. This is my true stress, isn't it? And of course here is my yield strength of the material. So see here, so here in the strain hardening region, as we know that from point to point, the stress is become more and more, isn't it? Because material is undergoing the strain hardening effect, and to overcome that, I have to supply the more amount of stress for the further deformation. So everywhere, see here, the stress is changing, isn't it? And to calculate the work in this deformation, I have to choose what? The area under of the stress strain curve, I will get the work done. Of course, in what? If this is unit, sigma t in the Newton per meter square into the strain having no unit. So definitely Newton per meter square. Strain is having no unit, but if I multiply and divided by meter, so it is Newton meter divided by meter cube. So Newton meter will be joule per meter cube. This will be what? The work under, or work for the deformation, which is nothing but the area under the stress strain curve. I will get the energy per unit of volume. Energy per unit of volume, which is nothing but the specific energy, that is energy per unit of volume. per unit of volume. See, up to the fracture point if I am going, so of course this is modulus of toughness. It is nothing but again energy per unit of volume. But here I am not interested in the toughness, I am talking about the work done. So see here. So here, say if I take this point, say here is the true stress is something, and here is of course very immediate point to that, again the increasing value of true strain is there. But what I am saying, that change is negligible. This change is very, very less. So simply if I take this, the change for the strain, that is d epsilon, the strip, okay, and I am saying that say sigma t here is same because change is negligible. So for this elemental strip, what is the work done here? How to calculate this work done is nothing but area under the stress strain curve, okay, for the small element, for the small change in strain. What I will get the work done here, that is the sigma t into d epsilon, isn't it? And please remember that here is very important assumption is that during the calculation of this work done, so the limit, so definitely if I want to calculate this entire work done here, isn't it, under this stress strain curve, so I have to integrate this small work done to this entire region, from where to where, from integral कहाँ से कहाँ तक का strain है. So actually I should take from here the strain from the yielding to this maximum strain. But see here, what the assumption is that we are assuming that the elastic strain is very, very less, very, very negligible compared to this plastic strain. So directly I am integrating this work for this work done from strain 0 to the required, 0 to required, not from the elastic to the required. Okay, so directly I will integrate from 0 to say epsilon f. So what is the work done I am getting here? Work done is equal to, work done in the deformation is equal to, we know integral 0 to epsilon f. What is that? Sigma t we know. What is sigma t value? K into epsilon to the power n d epsilon. So what I will get? So k into epsilon to the power n plus 1. See, variable is epsilon to the power n d epsilon. We are going to integrate this, divided by n plus 1, k is constant. And what is the limit? From 0 to epsilon f. See here, very important. So what is the work done I am getting in the deformation? What work done I am getting? That is k into epsilon f to the power n plus 1 divided by n plus 1. So this is the actual work done I am getting when the strain induced in the work material is up to epsilon f. Now see here, now I am going to introduce one hypothetical stress, that is the instantaneous stress for the further deformation. I am talking about the flow stress, the stress with which the material is flowing like a liquid, it's behaving like a liquid, that is the flow stress I am going to introduce. So it is, I am talking about not the actual values of the stress, but I am talking overall average value of one stress here, that is the sigma flow stress. So if say this is the value of sigma flow stress, okay, this is the hypothetical stress. Because of that, and this is the instantaneous stress, because of that the further deformation is possible into the work. So that this sigma flow is very, very important in many times in the load calculations, in the rolling, forging, in all these deformation processes we require this value of flow stress. So see, now we have calculated this actual work done with the sigma t stress, that is true stress. Now the same work if I calculate by the theoretical, okay, this is the sigma f, this is hypothetical stress. So again the work done will be what? This area under the stress strain curve. So what is this? Say length will be this and width will be this. Okay, so sigma f, that is the flow stress. So here see, whatever the initially missing here, now here whatever this area missing here, we have now assume here, see it is covered here. Okay, so the work done now are equal by actual, now with the theoretical what, the sigma f into epsilon, the sigma f into epsilon f. So this is the work done and this the work done, which are same. The flow stress, new concept, new stress is coming here. This is the hypothetical stress, which because of that the material is flowing like a liquid, it is deforming further and further. So here now we are getting the value of this flow stress. Please remember this flow, and how it is average flow stress I am talking about. So क्या आएगा यहाँ पे, this epsilon f and epsilon f get cancelled. क्या आएगा see यहाँ पे, I can write here, that is k into epsilon f to the power n into epsilon f divided by n plus 1. This epsilon f will come here, epsilon f, this get cancelled. So you will get the value for the average flow stress as k epsilon f to the power n divided by n plus 1. Please remember, and epsilon f is the actual or the final strain that is getting induced, sigma flow average. Please remember. So work done, you got it. What the value you get here? Work done is equal to k into epsilon f to the power n plus 1 divided by n plus 1, and unit will be what? It will be joule per meter cube. If I write here the value of this stress in megapascal, so megapascal में क्या आएगा? Work done, it is Newton per mm square into, I will multiply by mm by mm. But see, for getting this work done in joule, I have to convert it into meter. So it will be nothing but this 10 to the power minus 3 divided by 10 to the power minus 9. Okay, this mm cube. So convert करना पड़ेगा meter cube में, तो it will be 10 to the power minus 9. So it is equal to 10 to the power plus 9 minus 3, that is 10 to the power 6 Newton per meter square. That is 10 to the power 6, that is what? And this is meter upon meter, that is megajoule per meter cube. The unit, see, whenever the stress will be given in the megapascal, so what is the work of deformation? Work will be in 10 to the power 6 joule per meter cube, that is megajoule per meter cube. Please remember that will be the unit. Okay, so they can ask the question on this work done, or we require this flow stress for the calculations of load in the deformation processes. So dear students, please, these are very important things about the basics of metal forming. So we will take one or two examples on that, so that the basics concepts are get very much clear. We'll take it. So students, let us take this example. This is 2-mark question. So what is the question? See, the ultimate tensile strength of the material is 400 megapascal and elongation up to maximum load is 35%. It is given in percentage. If the material obeys the power law, then what is the true stress-strain relationship? And these are the options are given. So we have to put this stress-strain relation in the format of this power law or the flow curve equation, isn't it? Where sigma is the true stress, this value is equal to the strength coefficients, this epsilon is a true strain, and to the power these values are nothing but the strain hardening exponent. Let us see what is given. So see what is given here, the ultimate tensile strength of the material. So this is the nominal strength of the material, sigma n, as 400 megapascal. Okay, and elongation up to maximum load, very important word, maximum load. Okay, so here up to maximum loading, up to the where from here the instability begins, necking will start, isn't it? So we know that for that condition, here what is word, very important word, maximum loading. So at maximum loading condition or necking condition, what is there? The strain hardening exponent N is equal to the true strain. We have seen this, the instability in tension. Now here see, maximum elongation, maximum load, the elongation up to how much? 35%. So it is elongation given in percentage. So see, always percentage is related to the original thing, isn't it? So here this 35% is nothing but our nominal strain, that is 0.35, it is given. Okay, sigma n is known, the nominal or engineering strain is known. Now we have to calculate what? The true, that is the sigma t should be calculated. What is the formula? Sigma t is equal to sigma n into bracket 1 plus E, and true strain is equal to ln of 1 plus E, isn't it? So calculate the value of sigma t. Sigma t is equal to sigma n how much? 400 into bracket 1 plus 0.35. So sigma t will be 400 into 1.35. How much sigma t? 400 into 1.35, you get it as 540 megapascal. And here true strain, you get it as ln of 1 plus 0.35, that is ln of 1.35, you got it as 0.30. So epsilon true strain you got here 0.30, which is nothing but equal to the strain hardening exponent also 0.30, as here they are saying the up to maximum load, that is the instability condition is there. So epsilon is equal to n is equal to 0.3. So definitely one thing is clear, that epsilon to the power 0.3, out of this A and B there will be the one answer, isn't it? Because you got here n as a 0.30. Now see, we want the value of strength coefficient now. Okay, so you got the value of sigma t, that is 540 megapascal. So this sigma t, that is 540, is equal to this k into epsilon is how much? 0.30, and n is how much? To the 0.30. You will get the value of k is equal to, so 0.30 to the power 0.30, it is 0.696. This 540 divided by this 540 divided by answer, it is 774.92, which k nearly equal to what? 775 megapascal. So we get this value for the strength coefficient k, that is 775. You get this n value 0.30. Let us check, compare. क्या करना है आपको? कंपेयर करना है. What is sigma t is equal to k into epsilon to the power n. So sigma is equal to k is how much? 775 into epsilon to the power n is how much? 0.3. So this is the correct relationship. The 775 into epsilon to the power 0.30. This B is the correct answer. Very, very easy. You can get the relationship between the true stress and true strain by using the power law, the Flocker equation or the Holloman equation. Okay, let us take the next example. So dear students, let us see this another example, very, very nice example. See, the flow curve of the annealed metal is expressed as the sigma is equal to 200 into epsilon to the power 0.25, where the sigma is in megapascal. Please remember, the stress is given in megapascal. If the rod of this metal is subjected to a true strain, the true strain is given, that is 0.3. The ideal plastic work of deformation per unit volume. See, they are asking what? The work done in the deformation. Okay, so it is in Please remember, they are asking in megajoule per meter cube. Okay, and we have to write the answer there. So what is the work done? We know just now we calculated. It is K epsilon F to the power n divided by n plus 1, isn't it? So this is the work done in the deformation. We have seen like this. This is nothing but the area under the stress strain curve. If I take the elemental strip of thickness d epsilon and this sigma t as a stress, and see here how much stress is given from 0 to this is 0.3, epsilon f is 0.3. So and then work done is what? Work done will be equal to integral from 0 to 0.3. What is it? Is sigma t into d epsilon. So sigma t is what? K epsilon to the power n d epsilon integral 0 to sigma 0 to 0.3, which is nothing but K epsilon to the power n plus 1. Yes, divided by n plus 1. We will put the limits from 0 to 0.3 here. Okay, so here this n plus 1, isn't it? K into epsilon f to the power n plus 1 divided by n plus 1. This is the formula for work done. And this will be how much? Put the value of K here. So K is how much? Compare. We know that, see, sigma t is equal to K into epsilon to the power n. So what is K here? 200. K is 200. What is n here? N here is 0.25. And epsilon for what? It is given, epsilon f is given 0.3. So put the values here. K is 200 into epsilon f is 0.3 to the power 1 plus 0.25 divided by 1 plus 0.25. So we'll get like this, that is 200 into 0.3 to the power 1.25 divided by 1.25. So see, stress is given in megapascal. So stress is given in megapascal. So definitely the answer will become in megajoule per meter cube. Okay. So if I calculate this, so 0.3 to the power 1.25 divided by 1.25 into 200. So 35.52. So how much work done? 35.52. This megajoule per meter cube. This will be the specific energy. That is the work done. Plastic, ideal plastic work of deformation per unit volume. So कितना work done है यहाँ पे? आएगा 35.52. What is the answer here? 35.52. It will be in megajoule per meter cube, isn't it? So very easy. So like this they can ask you the questions. So thank you so much.